So, thanks for joining in to the linear structures session, which will be conducted using Hypermesh, and the solver will be OptiStruct. So today we've got Alex Quirk, who's a senior engineer of Altair here in Australia. But on another note, he's also had 6 years working for a number of different companies throughout Europe on a number of different projects, and he's going to take you through a bit of his time over there and the importance of the structural analysis and optimization in terms of automotive and how it can benefit your design. So please make him feel welcome, and thank you, Alex, for coming in today.
Okay, sorry, I was on mute. So thanks, Joel. As Joel mentioned, I'm the senior applications engineer here in Australia, based in Melbourne. I'll go through a few of basically how I got to where I am now, and the importance of linear analysis and optimization throughout product life cycles, and focusing on automotive for you guys. So, I went to university in the UK at the University of Leeds and studied aeronautical and aerospace engineering. I did my third year was part of a study abroad program at Rensselaer in New York in the US. And for my master's thesis, I did worked with EADS Astrium to design and develop a sample return mission for a Mars lander and sample return project. So from there, when I graduated, I joined Altair Product Design in the UK, based in the Midlands. And from there, I started work in the first instance with Boeing on their 787 project. But most of the time I spent working with Airbus on the A350, doing lightweight design optimization, and also using optimization to fix issues with the airframe. So I also worked with a number of the Formula One teams doing composite design and optimization, and then worked for about 2 years with Ferrari with their road cars division, developing new processes and techniques for developing road cars. And then finally worked with Augusta Westland Helicopters, looking at optimization of the airframe for their helicopters. And in each of these instances, we see not only good correlation to test for the analysis work we were doing, but even based on programs and designs that they'd come up with, which they thought were optimized, were averaging around 20 to 30% mass reduction without any detriment to the structural performance. So that's really what I wanted to show, how you guys can achieve those sorts of performance benefits for yourselves. So in April 2016, I've moved to Australia, now looking after the business for Australia and New Zealand. Based in Melbourne with Joel, and now responsible for consulting as I was in the UK, but also technical sales of the software support and training courses. And whereas as part of the product design team, we were working with one company at a time, focusing on and redesign of products. We're now looking after over 50 customers, including people like Ford, Airbus, Spirit, and the Australian government, Department of Defence, and BAE, to name just a few. So this is what you've all come here for today for, is to learn how to perform structural analysis and optimization using OptiStruct. So structural analysis is really where we spend most of our time, and OptiStruct is the #1 solver, other than for aerodynamics, that you'll probably be using throughout the design and development of these vehicles. So what are the key features So the first thing you're going to be looking at is strength. That's when we're looking at von Mises's stress or potentially failure index. If we're looking at composite structures, this will be a yield stress or failure stress that you'll be looking at to make sure that the parts can withstand the load. We'll also be looking at stiffness, so limiting the displacement, the rotation, or targeting a certain stiffness in bending or torsion. We also need to consider durability and fatigue. So, like I say, when we're looking at stress, if it's a part that's going to undergo very low number of cycles, then we can look at the yield stress. But if it's going to be something that's going to be under constant load, loading, unloading scenario, like you see from the cyclic load at the top there, then we need to consider the number of cycles that it's going to see in the lifetime, and adjust the stress accordingly based on the SN curve you can see there at the bottom. We also need to consider resonance. This can be very important for fatigue. If you have a resonant frequency, it can increase or decrease the fatigue life significantly. But also global fatigue can cause some issues for driver comfort and drivability. So it is also important to assess each part and the global performance for resonance. And then finally, on an individual component level, we need to look at stability. So this is whether under a compressive load, whether an individual component is going to fail due to buckling. So again, this will be a catastrophic failure mode, so it's very important to assess each component for the buckling. So that's the structural analysis part, and Joel's going to go through a lot more detail in each of those topics in a minute. So I'll jump straight into my area of speciality, which is structural optimization. So you'll see, a lot of you have seen from the Inspire session, that one of the key technologies within the HyperWorks suite is topology optimization. So this is where you can start when you don't know you've got no idea how you should design a part or what it should look like. Even if you've got a previous part that you think is poorly designed, you can start with topology optimization, which will come up with these generative structures which give you the optimal load paths. From there, if you're looking at sheet metal with stiffeners or doublers, you can use FreeSize to identify areas where you may need reinforcements and support. And then if you're looking at a stamped structure, you can increase the natural frequencies and the stiffness by stamping bead patterns into the structure. And our topography optimizer allows you to pick out the optimal bead patterns very quickly using topography optimization. When you're looking at more detailed studies, you can use FreeSize, which will automatically change the position of each of the nodes that you choose in order to meet your design criteria. So this image on the right is showing us an optimization changing the shape of each of those holes simultaneously with the goal or objective to minimize the stress in the part. So we can see it's doing a very efficient job of reducing those stresses without changing the design too much. If we want to parameterize our model in the same way that you could parameterize CAD, you can do this on the FE with OptiStruct. So you can control the shapes that are used, such as radius and thickness, in order to come up with a design that's feasible for manufacturing. And at the same time as doing this shape optimization, you can do size optimization. So if you're looking at individual parts that have constant thickness, they may be sheet metal or machined parts, you can optimize to find the optimal thickness for a given part. So generally, we'll start with the concept level tools and then progress on to the fine tuning optimization methods in the second phase for coming up with the final design. And the great thing about OptiStruct is once you've got an analysis model, it takes about 5 or 10 minutes to convert that analysis model into an optimization model, and allows you to pull out all the unnecessary weight. So a great example of that is the work we did with Airbus. It says on it was actually the A380, not the A390. Never mind. And you can see here where we use topology optimization in the first instance. We then come up with an engineering interpretation, not something you'd ever see on an aircraft any older than the A380 because the technology wasn't there. And then we use size and shape optimization to finalize the design. And in this instance, we pulled over 500 kilos per aircraft out of the A380 just by looking at the leading edge wing ribs, which is a huge amount of weight for an aircraft. I know a lot of you are using carbon fiber for parts of the design, so as well, there's no point using carbon fiber if you're not optimizing for it, because you just end up with black aluminium and you don't achieve the benefits of the composite material. So utilizing OptiStruct, again, we can use optimization to identify optimal ply shapes, the number of plies in each region, and also the laminate stacking sequence to come up with the lightest possible composite design. And with OptiStruct, we can even include things like foam cores or honeycomb into this optimization to really leverage the capabilities of the carbon fiber. A great example of that, again, from Airbus is the composite optimization we did on the underbelly fairing of one of the aircraft. So you can see here how we've gone through composite free size to come up with ply shapes, interpreted them into realistic shapes, and then done a sizing optimization and the stacking sequence optimization to come up with the final solution. And again, all of these examples are now flying. Every time you get on an Airbus aircraft or a Boeing aircraft, chances are something within that aircraft has been optimized using these techniques. Obviously, it's not all aerospace, it's just my area of expertise. So I want to show now the full vehicle level optimization work we developed with a certain European sports car manufacturer. It's now being used across Europe and across the world as the standard technique for vehicle optimization. So this C123 process is all about employing optimization in the first instance through topology optimization. So we're looking at full vehicle topology, similar to the way we saw in the first video I had up earlier. We then take those topology load paths from this optimization and convert them into 1D beams, and use optimization on the 1D beams. Now these 1D beam models take about 2 seconds to run. So an optimization goes through in about 1.5 minutes, which means you can go through multiple hundreds and thousands of different designs in a few days to come up with a really efficient structure that works for all of your criteria. And as you work through this, parts become solidified, and you decide on certain design aspects, and you convert those 1D models in C2 slowly into full fidelity shell and solid models, which is our C3 phase, which is then leaves you by the end of your concept development with a full fidelity structural analysis model. So this is a quick video of how this works. So we'll take a rough design space and rough loading and run topology optimization with a number of different settings until we come up with a good idea of how the structure should look. We then take this into C2 phase, where we do a quick interpretation in 2D and 1D beams and shells, which, as I said, can then be run hundreds and thousands of times to come up with a final solution, which then moves slowly as you get more confidence into what's called a C3 model, where we'll have full fidelity shells, solids, and 1D rigids. But by the time you get to C3, 90% of it is shells and solids. Very accurate, high detail model where you can run your vibroacoustics, you can run your crash, you can run your all your structural assessments at high confidence. And that's how we come up with the structural performance and the structural design for one of these high-end performance sports cars. And at the end of it, if you want, you can use Solid Thinking Evolve to render these models. It comes up with great solutions and makes everything look great. Obviously, it's been very popular with those OEMs. And to give you an idea, this is the statement from said European sports car manufacturer that we've been working with over the last 5 or so years. They said it's the most robust engineering and business case they've experienced to date. So I hope that gives you a bit of an idea and overview of how we use optimization technology. And obviously, if you have any questions, I'll be around on the webinar and happy to answer any questions at the end. So now I'll pass back over to Joel to go through the OptiStruct in detail.
No worries. Yeah, thank you very much for that, Alex. That was really good, and I hope everyone was able to take something out of that, particularly for the teams who are designing their FSAE cars. I hope that maybe down the track you might be able to implement some of that C1, 2, 3, or at least even be able to talk about it within your design and analysis phases. Could really sorry, just making sure my sound is on. Everyone can hear me correctly, yeah? Yep, sweet. Just making sure it's me. Okay, so we'll jump straight into it. So what we're going to go through today is how to set up a modal analysis, a static case with a force, and also a buckling case. How that then we can take those results, quickly understand the analysis of that, then put that into a free shape optimization case, and then obviously see the difference between the two. So I've already got my .fem model loaded up here, but just in case everyone missed it last week, I'll just quickly recap. For this one, as we are using OptiStruct, always make sure you go to the profile here with the little person, load user profile. And I always go to engineering solutions, aerospace, and make sure the drop-down box has OptiStruct in it. Loading up your FEM file is in File, go down to Import, and it's a solver deck. And make sure the file type is OptiStruct, and then you can select your .fem file from there. Okay, so where do we start with when beginning any kind of analysis? For me, what I will generally try and do is set up my material and properties of the model itself. So as this one is a FEM file, it's already meshed. So the meshing was done last week in the HyperMesh course. If you weren't here or able to miss it, your team leaders will have access to the recorded videos on the Dropbox. So what we're going to do is set up a property and a material for this model here. In the design tree here, simply right-click, create, and then we'll go down to material. So we'll just call this one steel. So we're just going to set up a basic steel material for this. So as you can, and then we go down further to the level here where we set all the material properties. As you can see, E, Young's modulus, and this is all in megapascals, by the way. So make sure you do know your units system that you are working in. And I'm just going to enter just some generic steel properties there, as you can see. So 21,000 for the megapascals, 0.3 for the Poisson's ratio, and then the density, which is all in kilograms. And I'm using megapascals because it's millimeters. And now what we'll do is we'll set up the property. So again, create down to property. So we'll just call this one the torsion link. So it always helps as well when setting these up, as after a while you'll have a number of different materials, number of different properties, making sure that you know which is which. So setting them up really well with specific names makes it much easier down the track if more than one person is working within the model as well. That's always a good handy thing to start with. So for this link, as we're not going to mid-surface it, because this is a solid torsion link, what we're going to do is a card image P shell would normally be used for all mid-surfaced shell element sections. We're actually going to change that to a P solid. So this says changing the card image can result in irreversible modifications to entities data. Yes, we do want to proceed to this because now what we're changing that to suit the element type and the model type that is set up here. If this was a thin shell element section or a mid-surface section with shell elements that I'm giving thickness to, then I always use the card image of a P shell. And so you'll also notice that we don't need to give a thickness because it's already through the model. And then we can actually define the material in this property. You don't always have to do this, but you can, depending if the material is always going to correspond to that property. So for this one, we won't. So what I'm going to do is then to assign these to my section is I click on the torsion link and then property. Just select both of them, and then you're going to select your torsion link property. And then below that will be material. And now we're going to select the steel. So now what we've just done there is we've just assigned a property and a material to our section. So now we're able to start building up the model in order to get it ready for the analysis. So I've already got two components here, one for RBE2s and one for RBE3s. Does anyone remember the difference between the RBE2 and RBE3 1D elements? So for the RBE2s, they transfer infinite stiffness, and RBE3s will transfer the load. So with this, because the section here is going to be fully constrained on the two large rear holes, we're going to be using RBE2s on the rear here, and then there's going to be a load placed in the front hole here. So to transfer the loads, we need to use the RBE3s. So what we're going to do is we're going to set up the RBE2s and RBE3s now. So we're going to make the RBE2 current by right-clicking on it and make current. And then we go up to mesh, and then we create 1D elements, and we go to rigids. So then down here, you've got a couple of different sections. You've got independent and dependent. So what we want to do is we want to change the drop-down box to multiple nodes. And then what we can do, because we want to find the middle node in the center of the circle, the independent node, I should say, in the center of the circle, we're going to have calculate node. So then what we can do is we can select a node within the circle. You can click on the actual node bit. I'll just go back on the node selection, and it comes up with a number of selections of how you can select it. So then we can go by face, and now it's automatically selected all the nodes within that section, and then we click create. Then if I pan this around, so holding control and the left click to move the model around, and then scroll in with the button, still holding control, it's made a single node in the center of that circle, connecting all the other nodes on the inside of the circle face. So we're going to do that again for the other one. Create. Okay, so we've got our two rigid nodes, our two rigid links created there. That will transfer infinite stiffness to this model. So what I'm going to do now is create the RBE3. So we want to change this one to that and make this current, RBE3 to current. You'll notice when it's bold, that's the component that's current. So we'll jump out of that one and then go back to mesh, create 1D elements RBE3s. And again, it does the same thing. So we want to have this on calculate node and independent nodes. So we shall select an inner face, biface, create, and it's done for us. And you can see the colors of these elements correspond to the color of the component, where the RBE2's color is green, the RBE3's color is yellow, and you can change these as much as you like as well, simply by clicking on the color. Okay, so what we're going to do now is we're going to put constraints on the rear holes. So on the two RBE2s, we're going to put 2 constraints there. So what we're going to do is we're going to create what's called a load collector. Again, right click in the entity tree, create load collector. So we're going to call this constraints. So we know exactly what's being created. And then we can go up to BC or boundary condition, create constraints. And now you've got a huge different selection that you can put in here. We've already got it on nodes, but you're able to put it on faces, edges. You can choose this to nodes, surfaces, points, and lines. But for this, we want to constrain the center node of each of those rear holes. So I'm going to click that. Now you can select both of these nodes at the same time. So now you'll see there's innermost white dot, that's the node selected, and then we've got degree of freedom 1 right through to degree of freedom 6. We want to have it fully constrained for this analysis, so making sure that they're all ticked will fully constrain them. And then we click create. Then you'll see this triangle now has created. This is showing that it's an SPC constraint, or it is constrained. So that is now our constraints created on this model. So now what we're going to do is we need to create a number of forces. So I'm going to create 2 more load collectors. So one's going to be the compression load, which I'm going to call compression load. And then another one is going to be a bending load. And that will be called that's going into component. We'll delete that. Now, if you want to delete a component, simply open it up by right-clicking on it and delete. So, create load collector, bending load. Okay, so now when you do this, I've run into this a number of times. I've created all my loads and realized I had the wrong one highlighted. So making sure that you definitely always check which one is highlighted prior to creating your constraints and forces and loads. So for this one, we're going to create the bending load. So boundary conditions, create forces. And again, we're going to put that on a node. So we're going to now put this on the RBE3. So I'm going to select the inner node, and this is going to be then 1e to the 5. So we can now choose the different coordinates. So I'm going to have it in the global system, and I want this bending upwards in the positive Z. So I've got my axis down here. I want it going in the positive Z. So I'm going to change that to So I'm going to change this, to the Z axis, and then making this 1e to the 5 and enter. And then that is there highlighted, so we zoom in just to check, and we've got the node highlighted, and then we create. Okay, and now what we can do, we can stay within this same page because we're going to create our compression load. I'm just going to change this to make the compression load current, making sure that that's bold. Again, selecting the same node because you can have more than one force on the same node. And I'm going to change that now to 1e to the 6, which means I just need to add another 0. But I also need to change the direction it's in, and which is going to be in the x-axis this time. So that's going to give me a full compression load because it is fully constrained at the rear. And we're going to create that. So now we've got our 2 loads created. So from this, now what we need to do as well is we need to create another load collector for our modal analysis. So what this will do, this won't actually have a force in it, this load collector, but this is telling the program to run the normal modes analysis on this part. So we'll create that and we'll go load collector, and I'm just going to call this modal. So for this one, we're going to give it a card image. So a card image is telling it that it is a specific type of collector. For the constraints and the loading, you don't have to do that for this time. But what we're going to do is we're going to give it an EIGRL card. So the EIG is from the eigenvalues. So if you're ever stuck with that, always think eigen, and then you should be able to get the RL out of that as well. So EIGRL for a standard modal analysis. So what's happened when we've put the card image in? We've got a number of things here now. So what I can actually do if I wanted to, in my V1 and V2, I can put lower and upper limits of the frequencies that we want to pull out of the analysis. But instead of doing that, what I'm going to do is in the ND section, number of routes desired, I'm actually going to tell it I want 12. So what this is going to give me is when this runs, will give me my first 12 modes. And it's very important to remember that with so we're not going to constrain this part in the modes analysis either. So remembering that the first 6 modes of this will actually be just rigid body modes and very low frequency. So they actually aren't real modes, but it is still an interest to see how the part is moving. But generally for everyone here, the first 2 real modes will be your mode 7 and mode 8, unless you've put a lower limit or an upper limit. Then you need to understand what your limits are constraining there. So for this analysis, we're just pulling out all first 12 modes. And we're going to keep the normalized to mass. Okay, so what we've done there is we've set up all our load collectors and constraints. So what we need to do now is we need to set up the load step. So this is now how it's going to be performing. So we're going to create a load step. And now what this will be is we're just going to call this just the compression load. So this will be our compression load in compression. So with the SPC and the load, so the SPC is just your standard constraints which we've applied on the RBE2s. So we're going to put, that's why another reason of correctly naming your load collectors also really helps as well. Because then we know exactly, we just want those constraints. Okay. And then the load, we know it's going to be the compression. Change the load collector to compression load. And then we're going to change the analysis type card. So for this one, we're just running a linear static case. And as you can see, there's a lot of different cases in here. But we're going to change this to linear static. And then we're going to do the same thing again for the bending. Whoops. So we'll create our load step, and this will be bending. Okay, and now we're going to have the same SPCs. So it'll be the constraints, only this time only the load will change, and that will be to the bending load. Then we change our analysis type to linear static. There we go. So now we've got a compression and a bending load set up. So actually, now one thing I forgot to do. So like the modal analysis, what we're going to do is we're going to set up the just jumping back to the load collectors, sorry. We're going to set up the buckling modal case. So we want to see the first 5 modes of buckling. So setting this up, I'm going to call it buck modal. And what we do is we set that to an EIGRL card again. Going to set my modes to 5. So I want the first 5 modes. And we're going to change the norm to max. So we're changing it from mass, we're putting it to max. Okay, so that's just, so we've got to set up that case as that load collector for the buckling mode. So back to the load step, and now we're going to set up our frequency mode, our frequency load step. So that's going to be a modal, normal modes analysis for our modal case. And then we're going to go into method structure. So not method fluid, this is going to be the structure where we select our modal. And I'm not constraining. If you want to do a constrained modes case, you can. You can put constraints in there, but for this one, we're not going to worry about it. I'm going to rename this. So if you haven't named your load steps or load case, you can always right-click on them and go to, not duplicate, rename. I'm going to call that modal. Delete that. Okay, so now we've got our compression, bending, and modal load steps set up. Is everyone sort of following this so far? Hopefully. Okay, so now we'll set up our linear buckling case with another load step. And we'll just call this buckling. Okay, so now we change our analysis type to linear buckling, which is here. And then we're going to go to our buckling section, so stat sub buckling. And also when you hover, if you're not sure what certain things are, when in these, you're able to hover over them. They give you a decent overview that might actually help you understand what they do and what they are. So for each different card, these sections can be different as well. So we're going to go to the stat sub buckling, and we're going to put in our buckling load step. Oh, what's just happened there? Whoop. Okay. Sorry about that. Just dropped down. So once you've done that, so I've got a few different ones here, but once you've set up that buckling, so we want to go, so we're going to, with our buckling in compression, because now we've got two buckling cases. You have your buckling in compression, so you set up your buckling mode in the in the method structure, you've got your buckling mode, right? And then in the stat sub buckling, you put the load case. So in the method structure, you've got your load collector buckling mode, stat sub, then you put the load that's creating that buckling. So that's why we're going to have two buckling cases, and then our buckling bending. So when we create our buckling bending, again, we create the load step, linear buckling analysis type, then we give it the bending static as the stat sub, and then the method structure is still the same buckling mode. So for both buckling modes, we're going to get the 5 modes out. So once all that's set up and you've got your materials and properties assigned, one thing you can do just to check is you go to Tools, then we go down to Model Checker, OptiStruct. So what this will do, this will give you a quick understanding whether you're able to run your part prior to running it, because sometimes there are small problems there that, very easy to fix, but you're not sure that they're there. It's always handy to run that. So it's Tools, Model Checker, OptiStruct, and in the Hyper Crash or Radios, it's the same in there, Tools, Model Checker, Radios, and which I'll go through next week. But we're going to run this just to see if there's any problems with the model, any problems with elements or things not assigned. It's always handy to do this. And as we can see, we've got green ticks among the boards. So we've got one cross here, an empty load collector. That's no problem to run with. It just means that I've got a load collector there, but it's holding 0 information, so it's actually not going to affect this at all. But the main ones here, because the warnings you can still run with, if you've got errors, the model definitely won't run. So we're looking all good there, ticks across the board. We've got our properties assigned, materials assigned, we've got all our loads assigned, constraints assigned, and all our modes and frequencies and ready to go. So what we would do then is we would go to Analysis, OptiStruct. You can go Save As, and then you can choose the path that you want to save the information in. Now, depending on your computer, you can do the line nproc space 4. So this is telling my computer to use 4 processors for this analysis. Set your export options, so you generally want to all or displayed, making sure you do know what's going to be. If you do have it set to all, or custom, I should say, custom, you can go to entity state here, and you can actually deselect what you would like exported. So if there's a component or a load collector and load step you don't want exported, you can click these and tell the program to not export them and not run that case. But for this, we're going to run everything, so I'm just going to change that to all. And then we would click OptiStruct, and then it would do the analysis. So, but in the essence of saving time, we won't run it physically right now. So once this is all run, we can pull up the results. So how you can do that is straight from the OptiStruct. You can go View Results, or you can open up what's called Hyperview, and then you can load the model and results using your .h3d file. So let's get into our first analysis of this bracket and understand what we're going to do with it and what's actually happening to it. So the first thing is this button here is the contour. We'll jump straight into that and click. So we've got it straight on displacement, and we're going to click apply. So what this does straight away is this gives just a first understanding of whether what you've set up is correct. Have you put the forces in the right locations? Have you put the forces on the right axes? Because sometimes you can get a displacement that is just not anything what you would think to expect. So you know then that you may have done a mistake in setting up the model, and you know to go straight back to it and recheck it. So it is always good to understand how the displacement is working. Sorry guys, it's just a bit slow. So also the controls for moving in Hyperview or HyperWorks are the same as HyperMesh as well. Always holding the control button and then the clicks to move it around. So as it expected, we would be expecting this to be pushed up in regards to the bending, and then it's also going to be pushed in towards the constraints from the compression. So we're not actually going to see, we shouldn't see any any full real displacement in the Y, but we can check that by changing the magnitude, and you can choose the axes that you want to go in. So let's just see what happens here in the Y without a force directly pushing it that way. And as you can see, because this is not a symmetrical part, that there is going to be some displacements, particularly on this side as well. So it's, again, you can either see the full magnitude of it, or you can see in certain axes. So change this back to magnitude, and you just hit apply, and that's how you can get a good visual on this. So let's have a look at the stresses. So this is our sub case 2. So here I haven't labeled it 100% correctly, so I can always jump back and try and find out which is which. So my sub case 2 in the load collectors is going to be my my bending static. So that means then so we'll jump back to Hyperview now. So the force that we're looking at here is going to be in the Z axis, and we're going to have a look at the stress. All right, so what does this tell us here? What we can instantly see is some really hot red spots in amongst near these corners here and through these webbings. So when we're looking at this, we need to also have we need to know how we set up our material properties, because that's going to tell us straight away, are we seeing failure in that section or not? And so in our material, if we've set it up with a yield stress or, a general steel case, basic yield stress is going to be around about 250 megapascals. Here we're looking at 282 megapascals. So we need to start having a look at this and go, right, okay, we are in the realm of seeing failure here, although it is only in a small area, but this is it's not something that you really want to be looking at all. You'd rather this to not be within the failure range and still within the elastic range, so within the range of the Young's modulus. So that's in our bending case. So let's drop down and we're going to check out our compression. Okay, so hit apply again, and making sure stresses are on 2D, 3D, and von Mises. So this is a real problem now. We've just gone from 282 megapascals in bending, and now our compression load is showing us a 761 megapascal stress within this inner web here. So that is, we know that is so far out of it, and that's not just within the plastic range. That's going to be probably full failure now. So we need to now do something about this. One way around this is, or there's a number of ways. Do we just change the material properties, change our materials? Do we just physically thicken the model? Do we try and make the model more symmetric? What do we do? So one thing is, obviously, we can apply optimization to this. We already know now that there's sections of it that are failing, but what do we need to do to that optimization? So one thing about that is we're going to have a look at our other cases. So let's go to our frequency. Okay, so we'll apply that and making sure the result type's eigenmode. So below the subcase, you've got the mode 1, and we can see the frequency is very low. It's at a negative 0.3. So remember how I was saying the first 6 modes, they're rigid body modes, and then after the 6th, the frequency we should see a large spike in the frequency, like a large increase, which we actually do here. So between 6 and 7 changes by, from negative 0.3 to plus 2. So our first real body mode is going to be a torsion mode. So it'll be mode 7. So let's just see what this does to it. So what we can do is we can just play the model, and you can have a pan around. You can see sort of how it's behaving under an unconstrained. So this is the torsion resonant frequency of this part with this material type. So it's really important to remember that between all materials, that will change the frequency as well. So we'll just slow that down a little bit with this little bar here underneath the play bar, and we can see it's slowed down. And then we're going to click the deformed button, and we're going to change the scale value. So we're going to put that to, say, 100. Oh, no, too big. So we'll put it down to 10. So what this does is scales the deformation by a factor of 10. So now you can get a good visual on how that resonant frequency is moving this part. So then we can go to mode 8. And this is now a bending mode. So as you can see, it's quite different, and we're seeing hotspots in much different areas. So again, this is another really good point to make sure you do understanding, because the resonant frequency is actually a first failure mode. Then we've got our yield stress, which is a second failure mode, and then the buckling, which is considered a third failure mode. So with these, we want to make sure that our resonant frequencies are far above any frequency that they would see during an in-service life. So we're going to pause that. Now we're going to have a quick look at the buckling. So we'll go to buckling compression, apply. So make sure you hit back to the contour. Then we're going to hit apply. Okay, so this here is showing where the buckling is occurring. Now, that's a pretty good spot, because that's the area of danger that we're seeing earlier in the static compression loading, where we're seeing the 761 megapascals. So it's pretty obvious that from this now that is a high stress area and a high area of buckling as well. So that's going to be the first part where it would buckle. But also, how we determine whether it's going to be buckling or is it going to be material failure. So what you can do is go through the modes. So I was on mode 5 there. But as you go through the modes, you'll see that the force is slightly different. So in order to create buckling in mode 1, with the force that was applied in compression, which was 1e to the 6, we would have to times that by roughly 25 times that compression force to actually cause buckling. And then, as you can see, we'll change the modes and it increases. So from that, now if this force was equal to exactly 1, that means buckling is occurring. So it's a big thing there to remember that when looking at these analysis, that if F is equal to 1, buckling is occurring. If F is greater than 1, you've got an engineering design factor increase there of the buckling case. So And now we'll quickly have a look at our buckling and bending. Okay, so this is slightly lower, but again, we're still higher. But we're looking at now 222 times that of the bending force to cause buckling in this case. So from this, what we've been able to understand now is our case of danger is our actual yield stress. So it's going to be a mechanical failure of the material. It's stable. The part is stable because it's not buckling, but we've also got some frequencies that we do need to make sure that we're outside of for all in-service parts. So how we use that for optimization then is we take this understanding, we go back to our model. Now that we know how this is performing in a static case, we want to set up an optimization case. So you'll see in analysis here, we've got optimization. So we click on that, and we're going to click the type of optimization we want, which is going to be free shape for this one. And you've got to create the design variable. So let's just call it free_shape. Nice and easy. Now, this is good because with free shape, you get to choose the nodes where you want it. So if you don't want to change the whole thing, but you just want to change those small local areas, all you need to do is, so if you only want to change this area in here, you just select the nodes in the region that you want to change with the shape. Or you can select all the nodes and then do the whole thing. So if we selected all the nodes, what my recommendation here would be, if everyone remembers back to the Inspire tutorial, how we don't do optimization on constraint parts, is you'd want to deselect these areas here because they do have constraints and loads on them. And then I would be deselecting all the nodes around that face as well. So what we will do is, we would then deselect all these nodes in each of these circles. Just being a bit wary of time here, so I'm just going to try and move a little bit quicker. So let's just say we're going to create that. So then we'll return back. Now we can create a response. So, we'll create responses. So from the response, we want to have a stress response because we know that that's a critical factor in this part. So we'll just call that stress. The response type will change from mass to static stress. Then you select your properties, and we've only got one property for this, so you would select the property of the material, and then we've got it on von Mises, and you go return or create. Now you can create a number of different stresses because we can also create for mass, and then we can change again this one to mass because we might want to minimize the mass as well. So we can have by total, you can choose the differences there, and we'll go create. So we've got a couple of responses created. Now we need to create constraints for those responses. So we pull the responses out from the analysis, then we constrain them. So for this, we're going to create this constraint for stress, and we're going to have an upper bound limit because our stress at the moment is far too high. So by selecting the upper bound box, we can then put in an upper bound limit. So we can put in a limit that is below our yield stress. So let's put in 240 megapascals. You can also select lower bounds. Now for these, you can put in you can do as many constraints as you want, but remembering that the more constraints you have, the more limiting the optimization becomes. So if you really are wanting to really push the mass down, maybe try having some less constraints, and then once you get it to a mass level that you're happy with, then you can start to re-optimize and redesign again. Or unless you are really happy with what you've got and you really want to constrain it heavily because you've got very little wiggle room for the design and the part, then the more constraints you put on, the more this will work with it. So then our response, we want to select the response stress, and then we create. And then you go to the load steps. So for this, for our stress, I would have my compression and my bending static, because they're the ones where I'm getting the stresses and the height. And then you go select and then create. So there, from the Inspire tutorial, remember how you always need an objective, you need some constraints. So there we've created a design variable. So for what we want to do, created the variable, we've created the response, and we've created the constraint. So what we need to do now is we need to create the objective. So remember, there's always a single objective in every optimization case, and for this we want it to be mass. So you want the minimum, and you can change it to maximum, min, max, but we want to do the minimum mass, and then you create. So there, what we've done is we've actually set up a full optimization case. Now, this is only one case. Remember, there's a whole range of different things that you can do with topology, topography, free size, free shape, and then all the different responses that you can create. Remember, this is just one way, and I'm just quickly showing what's there. So then you would rerun this analysis the same way I showed with the OptiStruct analysis, except when you go into it, you go analysis, OptiStruct, you run the optimization. So you can either have just analysis or optimization, or you can have check, restart. But for this, you'd make sure you have optimization on, and then you'd rerun it. So what you can expect to pull out of this. Okay, so what we can do now is we go the same way again. You'd open up your same results. We now open up our optimization case. So doesn't look much different here. No. What we'll do is we'll go to the contours. The result type will be shape change. We'll click apply. So as you can see on the design here, that's our variable. We're at iteration 1, so this hasn't changed at all. What we can do, if we change, so this is the way you can change from linear and transient modes. If we go to a transient mode, and we'll just slow this down, and we play this through, you can see, and I'll just slow it right down. So if you look up in the top right corner here in the graphics window, you see how the iterations are slowly counting up, and we can see how we're getting this more material added. So this is actually now showing how this is optimized for all our cases and all our constraints. So this has got to add material because it was so far in yield, although we've told it to minimize mass. So it's a thing to remember that, yeah, minimizing mass, you want it to be the lightest possible, but for all the constraints that you put in, it creates the objective for that case. So for our case, to get the stresses underneath 240 megapascals and to minimize mass, it's actually got to take some material from somewhere. So if we zoom right in here, we can actually see these flanges where the constraints are slowly thinning out. And what this is allowing is to then add the material into another section. So if we zoom into this bit, you can see where we're seeing back, like the 761 megapascals is getting extremely thick in here. So this is what we need to have a look at. And then what you can do as well to see how the run has performed. And also, and I'll pause that. So if you select down, this will show you every individual iteration that the analysis does as well. So we can go straight to iteration 20, which is the final one. And this is now showing us where material's been added, where material's been removed. And also with the legend here, one good way is you can change the colors of that simply just by clicking on the section you want to change. So I'm going to change the bottom bit, just turn it to a gray. And that helps you see where the material has been added by cutting out the medium blue to a dark blue. Now just put it the lowest case grey, and we can get a better look now of how this is actually being created. So another thing as well, there's around the holes of the where the constraints and loads are, those holes haven't changed because remember how we deselected the nodes? So it's very important, if those nodes weren't deselected, we would actually probably see some warping in there, like some hole size change, where if that's going to be like a proper constraint, say on the bolts and stuff, you don't want that to change. But if you've got full design changeability on those sections, and then it's always worthwhile leaving them in there and seeing how they perform as well. Oh, sorry. So that there is starting to show now what the optimization can do. Again, look, this is only one case. I mean, and under one condition. So you're able to constrain your frequency mode. So then you start to design your part around, the stresses and the frequencies seen. So you can put your frequency as a minimum, and you can say, look, or a maximum. You can say the maximum frequency coming in or the minimum frequency coming in will be this, and the optimization will then design around that to make sure that this part that you're optimizing doesn't see those modal frequencies, so you'll never hit resonance. And because that is actually a very vital case, as it is considered the first mode of failure. So in those FSAE cars, maybe fatigue life isn't one that you need to think about as much because you're only doing a few short runs, but maybe definitely the frequency that where you could quickly see a fast failure in a part is definitely one area that I would recommend looking into with these kinds of sections. So I'm aware I've just gone a little bit over time, guys, so I'll have to stop. I'll stop it there. Does anyone have any questions? I'll just reopen up the bar a bit. Does anyone have any questions about this? Because I know it's a lot to take in one go. Like the general training for this is a few days, and to cover it in only 2 hours, I understand it's a lot for Hypermesh and OptiStruct. So yeah, don't be discouraged if you can't get it all straight away, because it does take a lot of time. But I'm hoping that what I've been able to cover is showing all the tools, or as many of the tools as I can, that are available to everyone. And also remember that the Altair University has all the information on there for some training, for learning and help, as well as I'll jump back to Hypermesh and OptiStruct. And you can do this with all the solvers. In the open window is if you go to help, then you go to HyperWorks Help Home or OptiStruct Help. What you can get then is you can select the solver help that you want help with. You can select your OptiStruct, you can select, or even just your Hypermesh, and it can come up with a huge range of tutorials available for all different types of settings. So there is ones for just your linear statics. There's ones for non-linear. There's all tutorials set up, as well as you can find out about solvers. So you can look up, words that you're unsure of what they are. So if you're setting up a load step and you don't know what a card means, you can look at you can search for these cards in these help sections, and to get a bit more understanding of what you're looking at there. So, and also there's help in there to show you how to set up solver cards if you want to go more in depth, obviously without setting up a solver card. So this just gives you your standard stress, the 2D stress and strain, but I'll show you where all control cards are as well for any output. Control cards in analysis, and then you can go through all these, and again you can find information on all these different cards in this help section. So it really is a good handy spot to go. Even just check out global output request, and then you can select your C strain, your C stress, if you want displacement. So once you start selecting your own, the default goes out the window. So if you want displacement but you only select C stress, make sure you do select displacement, because it won't always output. So some of the default ones won't output when you start selecting like your own custom output. So make sure you select them all yourselves. Okay, look, I think that's probably covered more than enough for today. And I hope that you guys are starting to see some benefit as to where you might be able to start to implement these programs. But look, thank you very much for coming in, and hopefully I get to see everyone next week for the crash simulation. Yeah, so sorry, we did run out of time. I was meant to go through a torsion case. If everyone would like, I'm more than happy to do another one, another session this week that would take maybe about half an hour. Let me know, because yeah, we have gone a bit over time today, and I'm sorry about that. But the torsion case is to show how to set up a bending and torsion test of the chassis. So if you would like me to do that, more than happy to. Or if you want me to do it now, I can. I'm more than happy to stay around. It's up to you guys. So just let me know, yes or no, if you want me to keep going, or I can set up another session. Would everyone like me to do another half session tomorrow then? Like just another half-hour session and do the torsion test tomorrow? And I'll just stop the recording.